All right, let's get right into it. We talk to our AI assistants all the time, right? But what if they could do more than just fetch facts from the internet? What if they could actually use our computers for us? I'm talking opening apps, clicking through websites, editing stuff, all the things we do manually. Today, we're going to crack the code on how that sci-fi dream is fast becoming a reality. Seriously, just pause and think about this for a second. Imagine just saying to your computer, hey, find that picture of my dog wearing a sweater, open it in my photo editor, crank up the brightness a bit, and then slack it to the family. No clicking, no dragging, no hunting for menus. The AI just does it. And look, this is not some pie-in-the-sky idea for the distant future. This is happening now. Researchers, specifically at Microsoft, are building the literal nuts and bolts to create this kind of Jarvis for your PC, an AI that can see your screen and use it just like you do. So let's talk about the big picture goal here, the dream of a Jarvis-style AI. The official name for this is a computer use agent, or CUA for short. And its whole purpose is pretty revolutionary. And you know, I'm not just pulling the Iron Man reference out of thin air. The researchers themselves, in the technical paper for their new model Phi-Ground, they explicitly call out Jarvis. That's the North Star. That's the level of awesome they're shooting for. Now, here's the most important part, how it actually works. A CUA doesn't cheat by using some hidden code or secret app-specific APIs. No. It interacts with the screen, the graphical user interface, the GUI, the exact same way we do, by looking at what's on the display, moving a mouse, and typing. And that's huge, because it means it can work with literally any program, right out of the docs. Okay, so if the dream is so awesome and so clear, why isn't this on every computer already? Well, turns out, teaching an AI to do something that feels incredibly simple to us, like just clicking a button, is way, way harder than you'd think. This is the big roadblock. And this number, wow, this really puts the challenge into perspective. Before this new breakthrough we're talking about today, even the best models out there failed at this more than a third of the time on the really tough tests. That's just not good enough to be useful in the real world. I mean, can you imagine your mouse missing its target that often? The fancy technical name for this is GUI grounding. And honestly, the best way to think about it is as the AI's version of hand-eye coordination. You give it a command like click the save icon, and the AI has to translate those words into the exact pixel coordinates of that tiny little floppy disk icon on a super cluttered screen. Just look at this real-world example from an application. The instruction is simple. Click the shapes icon. For us, easy. Our brain just finds it. But for the AI, it's analyzing this whole sea of pixels and has to find that one tiny target based on nothing but a text command. That, right there, is the grounding problem in a nutshell. All right, so how did the team at Microsoft crack this nut? They realized that trying to build one single giant model to do everything was the wrong way to go. Instead, they came up with this really elegant two-step solution called Phi-Ground, and it's all about a smart division of labor. Think about it like a manager and a specialist on a team. First, you have a big brain planner model, something like GPT-4o. It acts like the manager. It looks at the whole screen, understands the user's request, and then writes a super detailed description of what to click on. Like, okay, we need to click the small blue square icon that's just to the left of the button labeled Arrange. Then, that clear instruction gets handed off to the grounder. That's the Phi-Ground model. It's the specialist. It does one thing and does it perfectly. It takes that description and finds the exact pixel coordinates for the mouse click. Bam! So what was the secret sauce here? What made Phi-Ground work so well? Well, this is where it gets really interesting, because the team made some discoveries that kind of go against what you might expect. And I love this quote from their report. They're basically saying that a lot of the fancy, complicated tricks that sound good on paper, well, they just didn't really matter once they started training on a truly massive scale. Turns out, with enough data, simplicity, and a few clever insights were the real keys to success. So here's a great example of that. You'd think, right, that to tell an AI about coordinates, you'd need some special complex computer language or tokens. But nope. They found the most reliable and effective way was just to have the AI spit out the coordinates as a plain old string of text, just like you or I would type 123, 456. Simple, stable, and it just worked better.
Data quality was another game changer. So if you just scrape data from the web, you get a biased data set where most of the things to click are in common spots, like the top left corner. And the AI learns that bias. It only learns to look there. So the researchers built a system to clean their data and make sure the training examples were spread out evenly all over the screen. This forced the AI to learn how to find things anywhere, not just in the usual places.
This one is so simple, it's brilliant. They found that the order you give the AI information matters. A lot. If you give it the text instruction first, say, find the blue button, and then show it the screenshot, its performance shoots up. It's because the AI knows what it's looking for before it even starts analyzing the image. It's primed for the task.
And what about all the different screen sizes and resolutions out there? This is a huge problem. They solved it with a cool trick called random resize, where they basically shrink the training images and put them on bigger backgrounds. And just doing that boosted performance on tricky, high-resolution tests by a huge 8%. So you take this new recipe, the smart two-step approach, the massive and clean data set, and all these clever training hacks. And the big question is, did it actually work? Let's look at the scores. The end result is a model that hits this perfect sweet spot. See, the goal isn't just to be the most accurate at any cost. You also have to be efficient enough to actually run on a real computer. And that's what they achieved. They hit what's called the Pareto frontier, which is just a fancy way of saying they got top-tier accuracy without needing a supercomputer to run it. It's accurate and practical.
And the numbers, well, they really do speak for themselves. On two of the hardest benchmarks for this stuff, Phi-Ground just blows the previous models out of the water. Look at that jump on ScreenSpot-pro from under 49% for the old model to 55% for Phi-Ground. That is a massive leap forward in getting the click right every single time.
So let's bring it all home. What does all this techie progress actually mean for you and me? It means we are one giant, tangible leap closer to that truly useful, Jarvis-like AI assistant we were all dreaming about at the start. So to wrap it all up, what are the big takeaways? First, that Planner plus Grounder team-up is a super effective way to build these things. Second, when you're working at a massive scale, high-quality, well-distributed data beats a complex algorithm any day. And third, sometimes the simplest, cleverest little training tricks can unlock huge performance gains. The bottom line, the future of the AI computer assistant is looking brighter and a lot more real.
And that really brings us to the most exciting part. Now that we've taught an AI the fundamental human skill of seeing and clicking with precision, the floodgates are open. The possibilities are kind of mind-boggling. So I'll leave you with this to think about. What's the first tedious, annoying, multi-step thing on your computer you're going to hand over to your new AI assistant?